Okay, so Miho, good morning to all of the people who survived till today. Yes, I'm very happy. Then today I will continue for some time the applications which I was talking about last time, and then I pass to present some more mathematical approach to Singularity. And then first thing which I want to say today, continuing, is the applications in so-called equilibrium state of conflict sets or of Maxwell sets. So if you have two centers, for example, from which there is expansion of the, maybe there are some types of people of some or some armies on there. So then they are just moving with the same speed on all directions. They have, that's enough. And then they are they're meeting on somewhere the same moment. You see, the same moment they met there. It takes the same distance. So there is this, and everywhere is like that. They met, so they met, they came the same moment. I mean, those who are going this direction and that direction, they came after some time to that point. They meet here, and this is a conflict. They stop there, and they cannot go further because this is just they met, and those does allow those to go there, and those does allow to go there for those. So that is the conflict set. So conflict set. So if you reduce the organizing centers to the points, so this is the line, just dividing the space equally. The distance is the same. And this is very good applications. It has, of course, many branches, but also in singularity theory, dynamics of that is very special. If you replace the points by the surfaces, because usually this is not necessarily the point, but some manifolds, then there is a whole geometry of these conflicts, objects, and so on. It's very interesting. Let's show you them. You can you can do this at home. Some simple programs, like you take. Now I show you the here. So you see you have you have the points, but that's maybe I start from the beginning. So let's forget of that. And so they take some centers, organizing centers, maybe some countries started at such points, sometimes long ago, in some small cities, and they expanded. And they think that everything belongs to them, but not, because there is a conflict set. The conflict set stops to expand. So this is 4, maybe 5, maybe 6. So you see so many tribes, I mean, people who are organized together, they expand. And then what is how does see the conflict of them? Because they meet sometimes together and start, maybe not to fight, but just realize that there is also other people who want to live and want to have space. And then this is compute. This is Voronoi, such mathematician, was considered such things. Oh, you see, if you calculate the set, it's looking like that. This is the conflict set between this organizing centers. Of course, if this is on the sphere, then you have to compactify this plane, and then of course this is not infinite, but grows on the sphere. But this guy, this country is very poor, has many neighbors, and all the press on it, of course, and then that's maybe this is not so nice situation. Then, of course, you can also consider. You see, this country might try to escape of that situation. It's not so easy. You see, that's not so easy. Not so easy. Not so easy, but maybe sometimes. And then there are such things like instability. You see, there is a unstable situation where there are 4 countries meet at one point. That's very unstable situation. Yeah. And also that parallelity is unstable situation. So then you see this is, maybe, of course, that's me. This is also very unstable situation when two are going through. Yeah, we can see how it is working. I mean, after some time, the borders, the conflict sets are changing. Nobody, everybody forgot how it was done. Yeah. It is, of course, choosing the different constants. This is the constant choosing situation. I choose another constant. So, and then this is why it's not easy to catch the point. As you see, there's the well, that's how how the centers organizing cells are moving. Then conflict sets are of course changing, and then there is a interesting structure of the borders of the countries and so on. Okay, on the sea, this is quite close to the reality. Okay, so this is you can just do such things, and they are very helpful. And sometimes in these generic positions, I mean, these peculiar singular positions. Many singular positions you can discover here, and then consider the kind of unfoldings of them, and then put to the reality and see that this is like that. Okay, so then maybe I pass to the presentation. I saw this was probably yeah. Yes, that's you already here. And now, you know, I would like to recall you this my presentation last lecture. So this conflict sets. This is something some generalization of the bifurcation set. What I told before. So on this you see this point this part of the bifurcation diagram is on this set where the minima are on the same level. This bifurcation set is called full bifurcation set because it is also, you know, this situation is also peculiar. I mean, it's also degenerate. Degenerate situation is in such point because this is, remember, the inflection points, and that part because this is the power 4, and that's also because they are on the same level. So we add this and call it full bifurcation diagram. And these are exactly the conflict points if you consider the or sometimes in physics there are Maxwell points, there's equilibrium of phases. In physics, there's exactly this this situation. If you have the physical potential, then the minima of the potential on the same level is exactly coexistence of phases. So coexistence means also conflict, but not in the pejorative. Then then the 4x4 set in higher dimensions for the swallowtail. So this is the Maxwell stratum, those who are between, you know. This is very useful and very well known in physics, in phase diagrams, but of course, here we have very systematic description of it. In this cell configurations and organizing centers, which I was talking about, the conflict set that are defined like that, you know, the distance. We should distance from the point, you know, such lambda that the distance are equal for 2 points pi pj, and always bigger than that for other points. This is definition of your conflict set. If you see, this is definition of conflict set. So there are also called sometimes maxims. And this is looking like that. You know, this so if you think that this is wave, which is coming there at the same moment on such thing, it depends, of course, on the speed, which is, if this is homogeneous, then this is different. Okay. And then there are diagrams and Euler formula also for that exists, but that's maybe another story. On the sphere, it's very interesting how does this work on the sphere. On the sphere, we have, we assume, for example, that we are interested in such cells which have isogonal, isogonal. That means the vertices are isogonal. So isogonal means like that. This is 120, 120, 120, and this is isogonal. You see, isogonal vertex. So this is like that. And then if you ask for such cells on the sphere, there is a relatively old answer that this is 10 such configurations. But proof was not long ago. I think that in 90s was proof, but already Steiner knew that the theorem in some way, but it's formulated. So there's 10 isogonal configurations of cells on the sphere, and this is this 10 isogonal networks. You see, the one is, of course, this one is relatively trivial because at each point, this is always isogonal, 180 degrees. So that is isogonal. So 10 isogonal. Then why I show this? Because of applications. Because sometimes if you have problems now, this nanotechnology is very blooming in some sense. A lot of achievements in quantum nanotechnology as well. But there are sometimes problems which, in fact, does not need a very advanced. I mean, completely not understood by physicists or engineers or mathematics, but just some tricky theorems which might be useful, like this one. So this is finite number of isogonal networks, and if in nanomedicine, in the I already told that in my first lecture, I think, when they try to find people try to find a transporter for the drug in the body, then that was very useful, this theorem, because told how to find some relations between big particles and small particles in the droplets. So then already I told that. This is in spherical structures. Spherical structures are very useful also, and then only that is what nature built us. You see, so often very isogonal, and also minimal shapes. Minimal shapes are defined as you see as an integral. You see this, they are forming our words in some sense. I told already about the critical points of functions, then of functionals, and so on. So minimum of such integral over a surface S of some integrand is here, depending on the tangent space to the surface. Then there's a measure on the surface. There's a standard measure, and every sum defined on the tangent space. So then there was proved already in the beginning of 20th century that the solution of this, depending on f, if f is constant, equal 1, then of course the solution of this problem is always sphere. Yeah, this is the minimal shape. But if this function is not constant, then that's a problem, or not problem, just has different shapes and kind of proof was that in some journal of crystallography source in Poland, that such set is just the shape, minimal shape, which is a solution of this problem. And I show how to construct. If you take f with some singularities just, then if it has singularities, then the shape has flat surfaces. So how to construct some f with singularities? Oh, and then we get, of course, anisotropy like that and so on. But that's and then I show you next program. Please. Okay. So now we is seen. This is everybody see this. This now. Okay. So in the solution of this minimal surface problem, which I told you, a wolf shape, this is easy to also to see that if you have f, it's a radial function because the tangent plane is defined by the orthogonal vector. So this is a radial function. So if you have the radial function, like for example that, which have singularities here, and this singularities, then you see that this is defined always as by everything. If you take off everything outside of this half plane, then finally you get something what is left here. And this is because of this integral. If you look on it, gives you such properties in such singularities, in such minima of radial function. The minima need not to be smooth. Maybe just continuous. That's even better. And then the envelope of these lines, in fact, defines the shape. So let me first construct this this curve. You see, if I constructed this f function as a moving this small cycle on the bigger cycle. Oh, this is not especially difficult, but you see it has some, as you know, this from school, this has some such singular points. And then you have, you take these lines, you see, these lines which I showed you. And then, of course, you can model it a bit. You see, this is even more, then you can take it bigger, and this is giving you, but moment, yeah, you see, oh, this is the triangle. If it depends on this on the singularities. So this red curve is the radial function f. Radial function f. This is just construction of that function, and then it is also construction just for computer, for the program that is easier to calculate. And you can see that, yeah, I can take more lines. If I take more lines, or less, more lines. If I take more lines, then that white one thing is just the minimal surface. Minimal surface. That's on the plane. This is such diamond, such shape, which is minimal in this sense. And of course, then if you take less lines, less tangent lines, and then you get something what you see exactly how it is. And if you make it bigger, I mean more singularities, then but this is possible to make bigger the shape. You see, you have okay. This is on the plane, so it's also it is such beautiful. So then you see such shapes you have, and how they appear in such shapes. You see the singularities here. This is some self-intersections there, and there's not at infinity, but somewhere far away. But there are cusps point, and this stuff. This maybe if I take it smaller, then will be more visible. No, it's one. Oh, you see, there's not only oh, this shape. This shape is not only, you see, the sides which are flat, but also this first one. See, this is very nice shape. And then there is a kind of swallowtail structure. It is hidden in some sense. It is invisible for the reality, but there exists, especially there where there are the sharp elements of the crystals. So the crystal shape is just appeared as the kind of minimal surfaces of some integral. Under integral is some tension, surface tension integral, which is physically introduced, and then it gives such shape, crystal, monocrystal. So this is very nice. Of course, you can can see some irregularities and some very peculiar situations which are given in singularity theory as degenerated, more degenerated. So then you see this. You can in fact construct quite many shapes. In 3 dimensions, this is more complicated. It's more complicated because you cannot so well see this. But you see this some shape which is this square. Of course, you ask why I took this this one cycle and the other side. This is only for technical construction of function, nothing else. Of course, I could even hide this because the problem is how does look like the function. If f is smooth, then of course we have no such beautiful effects, but also we have some effects. How does look like this set for fishing, for example? It depends. They're very well known in literature. The picture for fishing of how the fisherman should use his net to fish a maximal number of fish. That's also used there. So very interesting. So my lectures are only to convince you that this is a really beautiful subject, singularity theory, and you can construct it yourself. You can be independent researcher there. It's still an enormous number of questions. I mean, like mathematics. Mathematics is infinite. So only some people think that everything is known. Everything is known, yeah. Everything is known. Okay, so let's maybe close this program and and pass to the representation. And this presentation is maybe there, maybe. Yeah, that's how you have to see. But maybe I also will continue applications. So then, okay, maybe because I see that to the break we have 2 minutes to the break. Yeah. Okay. So I show you another application. That's here. Mm-hmm. Another application say, well, you can consider, for example, the waves on the lake. So you have, so let's say you have lake. See, this is lake. Yes, there is lake. See, it's lake. Well, of course, you can make it. You can more visible. This is the lake. Visible. You can see it from some distance. This lake might be like that, like say rectangular, or maybe like the cycle. This is maybe an ice lake. This lake, you see. And then, of course, students on laboratory are very interested to realize dynamics. What happens if what they do something? But in real, that's just a simulation of it. So then they just put the say droplets. So let's put say 2 droplets. 1 droplet from the up from the heaven. 2 droplets, and then okay, and then yeah, then let's start the droplets. You see the droplets. Maybe you don't see. Yeah, let's see. Then the droplets are just following down, and you see, normally it's like that. I don't know why it's so not so very well seen, but you can see it. Oh, this is the rain, but 2 droplets rain. Only 2 droplets are following down. But then, of course, we are just we govern this phenomenon. So sometimes, if you go with your colleague to the lake, you want to see more than only that reality, which is something. So you just change your viscosity. You see, if you change viscosity, uh, then your waves are not stopping, never. You see, they are moving and moving, and the energy is not dissipated. But that's it. And after some time, you see that some very interesting phenomena. And this is, as I told already, this object is not so easy because the solution of the wave equation, but on the plane. But this is also not especially difficult because it's possible to do that. After some time, you have such picture with 2 droplets and many reflections, many strange views of this situation. Because if you start to stop the energy, then after some time you have then you can see also the reflection. For example, reflection. The reflection. No, say you can put just 1 point here, for example, 1 droplet. What happens with 1 droplet? 1 droplet is not so many. And then I still 2 droplets. I still 1. Or maybe Yeah. So one droplet is just operating all the time. So then after some time, but the energy is pumped there by the droplet. So you can see its reflection on the water, the boundary of the lake. So the boundary is kind of mirror for the reflection. So you can see in the moment something looking like new source of wave. That's the reflection of this source. You see, there's a moment should be, but I don't know if this is should appear here some reflection of that. Well, at least after some time appears some reflection of this new source of that kind of the wave. Maybe it's also good to see this on the shape of rectangular shape. So then, if you send it from here, for example, then you also can see you see this droplet is somewhere there and producing the wave, but still energy is increased. So then the wave equation is has no dissipation of energy. So then this is moving like that. And after some time, this wave is reflected from the boundaries and form the kind of new point of focusing this energy, because the energy is pumped in that place, in that one source. Then this is moving. Very interesting phenomena you can see in this way by doing this by yourself. You see these waves are adding its energy, and then after some moment, you know, this is the another center of here of radiation. Yeah. This is not so easy to see, but anyway, sometimes the students wait a moment and prove everything they see better. You see, this is the organization of this lake surface after some time of too much energy pump. Okay, so then this is also this interesting project. Another project which I want to say was mechanics. In mechanics, there's the most number of applications of this story. And close this, unfortunately. No. Yeah. And then I show you the mechanical example. This is called Zeeman machine. Zeeman machine is some mechanical example. You see, this is maybe too small. Let me, if this is possible, expand better. Maybe I explain what is going on here. And then we have a disk. We have the material disk made of wood. Sometimes students are doing this for my talks. And then it is hardly attached to the blackboard, say, and this is blackboard, and this disk is made of wood or plastic, whatever. Sometimes they take just the compact disk and use the compact disk, too small, but that's okay. And then you see this is fixed. That my toy rotate around. And then they take always there, but take some nail here, keep the strong. This is some elastic thing. So maybe if I put it like that, or maybe like that, and then this and then this I keep it. That thing I keep. I take this, and this is elastic, this is spring, and this is spring, and this is fixed. And then if I move this on the plane, then this disk is rotating. It's rotating. And what happens? This is the simulated this problem. So you see, this one is fixed. This one is also fixed, but to the disk. Disk is this one, and that I keep and move. So let me move this. Let's work with stuff. Or you see, I move this, but some way, because it calculates. You see, this calculates this state. So you see, this is the elastic. You can imagine that is fixed here. That's my rotate. The disk might rotate. So there are two strings or two elastic. And then if I move like that, then this is also moving. You see this? Yeah. And then what happens if I pass through? Oh, it's a very big change. Of course, this change is in some sense stopped by friction, by something. But if you reconsider the static, I mean not dynamic problem, then we have more. You see, dynamic is not using this waving around the fixed point, around the minimum. So then it's immediately in the minimum. So then you see it's not and not off. You see, this is the very big jump. So then if you are going here, there's no jump, no, there's no jump, even here is no jump, you see. But if you go here, oh, it's jump, smaller jump. This is just, so if someone is, you see, if someone is standing on the disk, then at some moment it is falling down because such jump is huge. It is not an earthquake or something, but it isn't. But it is done by move of this yellow point on the plane. So what is this? This is again the experimental finding the catastrophe set or bifurcation set. There is some set here. It looks like that. I cannot draw picture here, but like that. And maybe I draw here. So this set is looking like that, and there's a 4 cusps. And if we pass through this cusp here and here, there is a huge jump of this disk. This is why, and in mechanics is the singularities catastrophes are very, very often, and in fact. In small dimensions, it's easy to do. In the high dimensions, it's more work, more difficult. So you see, then if I do this here, there's there is also, so this is that, and then another one is. I'm passing through these cusp points. If I pass here, then it's not the catastrophes. And also here. These are these two, and then this is very small. On that plane, which is calculated here, it's quite small, this set. But there is. Did you jump? Then, yeah. There are two possibilities. Up and down. So this is, if you are far away, then no problem. You omit this, you just avoid this. So this is what is important for applications, that we find this set, bifurcation set, then we know what to do, where to go, not passing through it or passing through it. So this is in application medicine, anorexia nervosa. In the 70s, 80s was very successfully cured by English group of doctors using just the model of anorexia by Zeeman and its collaborators. So this is called Zeeman machine. Zeeman was a British mathematician who was very famous. Okay, so then yeah, there are also some interesting applications. That's yeah, great. So let's now. Okay, so we start. So let's come back now to mathematics, in which is behind of the all applications, which I didn't talk about most of them, just only example. So uh-huh. Okay. You didn't full screen. Oh yeah. Oh, so then I also already talked about that. This we start with the critical point of function. Critical points of functions. You have a function on Rn. I already talked about functions on Cn and so on. Smooth real varied functions, and P is a critical point of f if such differential is vanishing. That means that all partial differentials P is vanishing. P is a single point of f if and if the first derivative is partial derivative is this here, that's n is vanishing, and the determinant of the second derivative, the Hessian matrix. The determinant of the second derivative is called the Hessian. And this is also vanishing, and such point P we call a singular point or degenerated critical point, singularity. Singularity is if the second derivatives are vanishing. And we call it Morse critical point if this Hessian is non-degenerate, so that this Hessian is non-vanishing. So, for example, this is the case. Point of x1 square plus minus x2 square is a Morse point. It's a Morse point. And there is a natural theorem. Theorems are just very intuitive, so I don't need to go through a long time on them, that all critical points of typical functions are non-degenerate. So that's what is typical. Typical means that if you, something is typical. For example, typically people drink Coca-Cola. Yeah? Some only people drink something different in Europe. So this typical is something that if you exclude the set of codimension bigger than 0, then you get just these elements. So so typical functions are non-degenerate. In the neighborhoods of such a point which is non-degenerate, there is always a smooth change of variables. No, you saw this H smooth, so this does the diffeomorphism, the mapping Z1 into x1 to xn. If you replace, for example, z by x, then you get new function f, which is some number, and you have only squares of variables, and part of these squares with minus and part of these squares with plus. And this is an index of, it's called index of the critical point, of index of the more critical point. And then, of course, this looks like that. One variable is like that, but of course, if more variables, it's more complicated. This index, yeah. And then now, if we have such functions, then we see that these critical points don't generate or degenerate or non-degenerate. They are kind of situated locally. We observe them locally, we change variables locally in some neighborhood and so on. So we can say that some equivalency, we can recognize points together with their small neighborhood, open neighborhood. So we define some equivalency relation. So F and G, this is in mathematics very common, but something we don't say about that. F and G, they are smooth functions. We call it the right equivalent at some point P. At some point P belonging to Rn, if there exists a diffeomorphism, which is transforming Rn into Rn, preserving point P. A constant K, such that F is equal G, composed with H plus this constant K. And we already in applications, yesterday, I already defined the equivalency of families and so on, using the diffeomorphism, very special. But here, very, very natural diffeomorphism, preserving P, we call it, later will be some notation of jars. And then we call that these two functions are right equivalent if we find at point P, say, that if we find some diffeomorphism preserving P such that these functions are related in this way. Yeah. No question? Oh. Not yet. Of course, many of these relations we always study. It depends on the context, or the spaces, on the and so on. But here is the simplest one, right, because from the right, acting from the right. This is left, this is right. This is why we call it right. And if F has a Morse critical point at 0 with index K, then F is right equivalent to such form. Such very simple squares. Right equivalent, that means that there is some neighborhood in which this is possible to do this. And if this is, these are not functions, but mappings, if they are mappings, then the situation is even might be more clear. Yeah, but also easy to define what is important. So if we start the singularities of mappings, then we introduce the right-left equivalence. Left because also from the left. This is left of G, this one, the right of G, this one. So then we call it F and G are right-left equivalent. These are very common equivalency in singularity. Then if such diagram is commuting. It's a commuting diagram means always that this is quite strong property, that if you go from this space to that space, you go both ways to the same point, always. A right equivalence is only acting on the right. Yeah. If this is so, then this one is identity. Maybe, if you like, yes, but that was defined before for functions. But this is for mappings. We have no constant. Because to mapping, you cannot add constant. What is that? Constant is a very, yeah. So, but right equivalence, if you just identify these two things, then you have only psi. But then also there is left equivalence for functions. But I didn't. But this adding k is also considered left equivalent. But we don't say so. But only add k. But it's possible also to define right left. For mappings, it is most for functions. It's not so useful. Left equivalence is most of functions are if they are right equivalent, then right left equivalent, then they are also right equivalent. Especially this homogeneous homogeneous function. So that is the same. I mean, that is why we don't use always the left equivalence in functions. Okay, but then we have it. Definition is here that f is right left equivalent to g. Now, if we go in this way, so then we go the same. We go in this way, which is exactly that. So g, you see, composed with phi. So then it's something like you apply the here, and then you have this is a phi, psi, then go by g, and then if you compose psi here, you see psi here because it's psi to -1, because I applied from the left psi -1. Then this is psi composed with f. And then this is the same. That means that if you apply point to f this way, and then through psi, then you get this one. But then I apply to both sides. Maybe I write this on the blackboard. Oh, visible. So G composed with, and then here is psi composed with F. Then this diagram means that one. But if I apply here, say, -y from left side, of course, here I have identity, and I have F is equal psi -1, G psi. This is nothing else. So this is why we do, this is left equivalence. And both of these are diffeomorphic. Of course, if this we have continuous situations, homomorphisms and so on. Stability. Now the intuitive also the definition of stability of Morse critical point. In Morse critical points, we have first derivative and second derivative. And second derivative is not degenerated. Say if there's a Hessian matrix, then this is maximal rank and so on. So if f has a Morse critical point at p with index k and g is a small perturbation of f. So what does it mean? G small perturbation of f. That means that g squared g are close to f, gf, g to f. Close. Maybe some epsilon, delta, rho, which are very not so big numbers. Or if they are big, but this is a zoom, and we don't know what is big in general. Then G also has Morse critical point with index k. So if these things are relatively close to each other, then a point of f also a function f also has a critical point of Morse type, and that means that in some point q near p. I cannot remove this. Then and then that means that if you perturb slightly, then there's again minimum or maximum or something or critical point of index k, but close. Some q. You find the point q in the neighborhood. So then this is In my book is definition, but you can translate it easily by translator, perhaps, in sense more. Say example. Here example is here, which I already showed, is x cubed over 3 has singularity, because this is the generated point, critical point at 0. And it is not stable, because if you have a close, those things are very close, together with even with third derivative, nevertheless, they are not, you don't find such point in the neighborhood. So that this is because of this perturbation completely destroy this x cube. It's never appearing, you know, in this perturbation. And any of the perturbations, in any of the perturbation of x cube never appear. So there's the only Morse points are stable for functions. The others never are stable. But doesn't mean that they are not important. They are very important, even more important than stable, because then stabilized, they give a new dimensions and new words. So that's just what René Thome emphasized, that the most important points are just non-stable. Okay, as a small perturbation, for epsilon greater than 0, G has 2 Morse points at plus minus square. You remember I calculated it. And then for epsilon less than 0 has no critical points. So that's always like that. So and this is just picture. This is just picture of that situation. You have this x cube over 3, and then it's distant or distant. Or you have x to power 6. If you have to power 6, then you have this to power 2 squared, then you have 2 minima, 2 maxima, 3 minima, and also 1 maximum, 2 minima. There's many perturbations of this, which are not so many, but finite number of perturbations of this x to power 6, which is also non-stable, but scatters into much more stable cases. All these things are stable, but if these values are not on the same level. If they are on the same level, then of course they are not stable. Then perturbed further disappear this common level. And there is also the theorem, which is so important. That theorems which I say, there are just folklore of the mathematical singularity theory that I know for everybody. So all typical functions on compact manifold are stable. Of course, that's obvious. Compact, because if you have not compact, then some phenomena may have. The set of unstable functions has codimension greater than or equal to 1. So there is some constraint, which is some condition you need to fulfill that the unstable functions you find. It's not just that if you just choose by chance something, then you always choose the stable. Unstable are in some small set. Yeah, that's a good question. This is a good question, because this is the difference. For example, if you have the plane here, so the codimension of the curve is a dimension of the plane minus dimension what? Yeah. So dimension of the space minus dimension of the curve. So you understand? Then here is 1, of course, 1. But the interesting thing here is that dimensions of both spaces are infinite. So you have something like that. Infinite minus infinite equal 1. And this is interesting. You know, and this is possible because you can, what does it mean codimension 1? There is a one condition, for example, on the functions. If you have, say, functions like, I will formalize this, all functions, terms of functions soon will be germs. Then you have all Taylor series. Then you have coefficients, infinite number. Yeah? So then if the first coefficients are vanishing, then you have one dimension less. You still have infinite dimensional space of functions, but less or less one dimension than all functions. This is why we call it codimension. This is very big, very clever approach to singularities. Singularities we can investigate by codimension, not by dimension. Dimensions are infinite because you have a huge spaces of functions. You can only say about codimensions. So this is all the time in Singularity. You have codimensions, 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 and so on. But this was a very good question. But of course, in the finite dimensional case, but you need not to talk about codimensions because dimension is the same good. But how to tell about dimensions of all smooth functions? Just there is infinity. But codimensions this is possible. And then a function is stable if all its critical points are non-degenerate and the critical values differ. This is just summarizing what I told you. Example. This example is calculational example. The numbers of non-equivalent stable functions on the cycle. You have one-dimensional cycle, which have 2n critical points for n equal 1, 2, 3, 4, and so on. These are coefficients of the tangent, expansion of tangent, trigonometric function tangents. So, yeah. Now, let's pass to because we are interested in local now investigation of critical points, then let's pass to the definition of new definition. We have first C infinity functions. So that's, you know, I should maybe say that since you remember maybe the ancient Greeks mathematicians, so the famous one or the only one was who started this was Pythagoras, if he exists, and he thought that all world is built of numbers. But the next one but he thought about some say static world. But the next one who thought that all morphology and morphogenesis of this world is built of smooth functions was just René Thom. There's another Pythagoras of the recent time. He thought that every morphology and morphogenesis, so whatever you have a phenomena should be, there are elements of the C infinity functions. So that means infinitely many differentiable functions. There are, you see, before we had 2,600 years before, we had the numbers, now we have smooth functions. After London, not complex analysis. But some people will be unhappy if I say so. But that's, of course, complex. Maybe. And we say that we define the localization of the function. I mean, f and g is equivalent at 0, say, if there exists open subset of 0, such that these two functions are equal on that subset. Now, let's draw a picture. So, you see, on some open neighborhood, these functions are the same. then they are equivalent. In this sense, they are F0 G equivalent. And class of equivalency of such functions we call germ. Germs are, they came from complex. This is in fact the germ of function f at 0. So this is equivalency class of f at 0. So you see, this is a kind of something like that. This is very strange object, the germ. You have infinitely many of elements in the class of equivalency, but all of them, they have such property that if you take two of them, there are always an open set on which they are equal. So that's very important. So because, and usually we take representatives of such classes. The same with mappings. So we have we denote that E, C, calligraphic N as germs of mappings, and then one is functions. For example, here you see, if you take function f minus x plus x to the power 5, the germ of this function, you consider germ of this function, then certainly x squared doesn't belong to this germ. Yeah, you understand. Because not only this function doesn't belong, but you see, this is something like that. If you add x5, then there is something. But then x squared is something like that. So no chance that it is equal to on some open neighborhood to that function, because this is transversal even, the graph. So that's impossible. So then the germs are on, that's, you know, this is the germ. Germ is a kind of like, you know, very complicated object, but very easy, some basic understanding. So now, if you have singularity, then the very important idea was gas unfolding. If there is complicated, very degenerated singularity, and is simply this different. So you see, we have we have a germ of function now. This is function, and then n dimensions, and we call we take f big F. You see, unfolding of eta if f is smooth germ also, and f restricted to first variable is just eta. So that means that you have this f on xu. This is the graph. It's like that. It's quite big because extended in r parameters. And if you consider intersection of it by u equals 0, you have to go eta. So eta is this function, and the unfolding is this in all dimensions. So then sometimes some person is very singular and he needs more dimensions for his life, and then he is satisfied. So that is unfolding. Yeah. So that's formally is very simple. Yeah. Yeah, very simple. There's not any transformation. So that's extension for new into new dimensions. And then example, we already took it a few times. This is unfolding, you see, of x to power 3 unfolding. If you add lambda, or that is unfolding. Of course, it's not written here, but lambda, but this is, yeah. And now, if we have these unfoldings is again a huge space of unfoldings. So we have categorical approach to that. Was people who like category theory, which Singularity also say, because in category theory there is a final object. If you have morphisms, then there is always good category theory. There is object to which all are morphic. So then we have germ, eta, and all his unfoldings, or her. Germ is maybe her, or he, I don't know. Morphisms. Morphisms, we have to define morphisms. Morphisms is just the search diagram which is commuting existing search diagram. So we call that, you see, RF is induced from SG by the morphism phi big one, phi small, and epsilon, if such relation is fulfilled, which is exactly commuting of such diagram. And so there is, and of course, these guys are mappings. I mean, these morphisms, especially this one is family of different morphisms. So this is definitely it's a category. Oh, I don't know why this is not. Oh. But yeah. Oh, and then next one, this one. Yes. Maybe I prefer by arrows. So so then if you have this categorical approach, then we have the notion of universal and versal. Versal is a maximal in some sense, that all others are mini-versal, is such that has a minimal number of parameters. Because versal cannot have, need not to have a minimal number of these parameters R, but mini-versal has to have this minimal of parameters. There's examples I give understand easily. So RF is called versal unfolding if eta of eta, if any other unfolding of eta can be induced from that one. So that's very simple definition. Versal unfolding is such one that all other unfoldings are induced from it. In some sense, they are sitting in it. So this is versal. So this is from category RF is called universal or universal, but universal of eta if RF is versal and R is minimal number. But then it's uniquely defined. Universal is universals. Mini is uniquely defined. An example, for example, you have x to the power k if k is greater than 2. That this unfolding you add with parameters powers of x is mini-versal unfolding of it. How to prove it? That's other story. This is not so easy to prove it, but this is example. So this is really mini-versal unfolding, universal also mini because it has minimal number of parameters, but this is the same like universal, and all other unfoldings, which might be at again infinite dimensional space, are induced from that. So this is, it's the beauty of this. And now to study that, to study this, especially this how this codimension or spaces, we introduce jet spaces. Jets are very useful in this theory because these are that's not especially difficult. First, we define the space Nk, and I want it's a functions for mappings is the same. Such functions are terms that their derivatives according to k are vanishing. If they are vanishing, no, then the space of jets, they are just nothing else but extensions of the function with Taylor series coefficients to power k. This is all. This is why this is less than or equal to k, because this is one more is just the started. So all this to power k of anything. I mean, if you take a modulo of this space, then you get all Taylor series to power k. And this is a space of jets. Space of jets. By space of jets at zero, you can take a spaces at each point. You can have extensions of jet spaces and so on. It's a very fundamental and very important object in singularity theory. And of course, for this quotient space as a canonical projection to each function for germ, because this is for germs, you prescribe the jet. It's jet, k jet. If this is jk, is this fundamental projection onto classes this quotient space. And then En is local algebra over R. So then this space of germs is a local algebra over M. So then there is, because this is local, this has only one uniquely defined maximal ideal. That is all germs, you see, defined by representatives which at zero have zero. So this is maximal ideal. And then using this maximal ideal, we can define this. So that will be the N by maximal ideal to power k plus 1 and so on. So this is local algebra here, very, very well used. And then now about this equivalence of germs, which is gives a classification of singularities. So we introduce the germs of diffeomorphism, so preserving zero, because that's classification group. And then this is, of course, this algebraic group means that there are conditions for it in the space of terms of mappings and N. And then we say that two germs are equivalent if there exists germ of the diffeomorphism gamma belonging to gamma N such that eta is just psi composed with gamma. For example, this one, eta and xi are equivalent if A is bigger than zero. If A is less than zero or zero, they are not equivalent. No, that's also obvious because this is a Morse function. This is positive, then always you can change variables, take it under the square. If this is minus, then you cannot do this. So the minus here and plus here is excluded from the equivalency, so on. So this is just the simple calculations. And now it's very important notion which you study singularities. This is just the k-determinants of sufficiency of jets. So we count this k equivalent if they have the same k jet. So if they have the same extension to power k, then we call them k equivalent. Oh, there's another equivalency. We have many equivalencies here. And then eta term is k determined if for every psi, any other psi, we have something like that. If psi is k equivalent, then it is equivalent. Right equivalency. This is only right equivalency. Yes, right. Because they're functions. Yeah. But what? So that means that if you have the g eta and it's yk was equal yk of psi, then eta is equivalent psi. That means that eta is equal psi superposed with gamma. It was on the previously. So you see, then we call it k determined. So then that means that if you take this Taylor series extension to power k, to power k is completely defined. That means that whatever you add, so for example, you have the eta is equal sum on alpha I, x to power, that's one variable, to power I equal, say, 0 to k, plus f on x, where it may be plus x to power k plus 1, f on x. It's better like that. Look, then this one has no meaning. Always you can change variables that there is only this extension to power k. So that means that the function is defined only finitely by a finite number of coefficients. Of course, very big, maybe long, very long, but finite. Well, this is k. This is very important. So that means that kz is sufficient. What does it mean? You know, if you have a function, for example, sinus x, you have this, of course. Well, maybe this doesn't matter. Well, you take this sinus. Maybe it's not so good, but. Because someone will think that the trigonometric functions are this. No. Let's take function, say, x squared plus x to power 100 plus logarithm, and so on. Then you see plus 5x to power million, 1 million or something. So then you see this function. This is function eta, and its 2z is sufficient. So you don't need to consider the rest of this. You just take your square eta is equal x square is enough. I mean, this 2z determine completely this function. You understand? Doesn't matter what you add higher. If you add something like plus x cube or plus x4, whatever, with some coefficients, doesn't matter. This germ is the same. This is sufficient and is k determined, to determine. You understand? Yeah. Yeah, that's good. Yeah, and this is why we call the jets sufficient. So maybe I quickly go through. And then we continue tomorrow, and then that's a sufficient condition for this k determinacy is very important. Maybe I continue next tomorrow. So that's very easy also explain. Good if people have questions, because then other people can understand better. Oh, thank you very much. Thank you for all of participants. Oh, this is R field, but you can consider C as well. Yes, algebraic close. Yeah, that's only such field. R field is the same. If even in some sense, even because you know in a complex in holomorphic you have no flat function, but you have flat function. If you have a flat function, what is flat function? That all derivatives are vanishing, but function is not vanishing. But in holomorphic, of course, this is. So this is smooth functions. This is why René Thom formulated this. So René Thom is Pythagoras too. Why, of course, so do you understand? Yeah. So You mean, what do you think? They play some important role, but this is not. Yes, they play. For example, Weierstrass preparation theorem was for analytic functions, but for smooth function was very difficult to prove it. It was proved, and then it appeared that this was very successful. I mean, this thing here. So, oh, very good that you are right.